Hello and welcome back to the Hutchins School Chemistry Lab. I'm Dr. James and today we'll be talking about the structure of benzene, and we'll talk briefly about how the structure of benzene affects its reactivity. Let's get to it. This is the chemical structure of benzene. You can see that it is 6 carbons in a cyclic formation with alternating double and single bonds. Each carbon is attached to a single hydrogen and 2 other carbons. There are 2 different ways to draw this structure. I've got some helper structures here. I have arbitrarily marked a carbon in the structure of benzene, and you can see on this left hand side we have to the left a double bond from that blue carbon, and on the right hand side we have the double bond to the right. What this is showing is that there are 2 different ways that we can draw this structure. They are equivalent and there's no difference between the 2 of them, although it's true that chemically both can exist. Now we're going to talk a little bit more about the implications of those 2 structures, but in essence it's going to add some stability to the compound. So the question remains, what actually is a covalent bond? Well, you can't see a covalent bond, nor could you touch one. Covalent bonds are simply the distance between 2 nuclei. In hydrocarbons, a standard double bond is 1.34 angstroms. Now 1 angstrom is 10 to the minus 10 meters, so this is 1.34 by 10 to the minus 10 meters. This is a small bond distance, which represents a double bond. A larger distance, such as 1.54 angstroms, would represent a single bond. The distance between nuclei is determined by the amount of electron density between those 2 nuclei. So when we have more electron density, i.e. a double or triple bond, we have more negative charges between the positive nuclei, and those more negative charges allow those positive nuclei to get closer to each other because obviously they're attracted to those electrons that are shared between them. We're going a little bit deeper than I would expect you to be assessed, and certainly I wouldn't anticipate that you'll be assessed on bond lengths. However, I always find that if I understand where things are coming from, I can remember them better. At a more fundamental level, chemical bonds are when one nucleus shares one of its electrons with another nucleus, which is also sharing 1 electron. That means that a chemical bond must be made of 2 electrons. And a further point of interest, when we have a single bond between 2 atoms, those 2 atoms are free to rotate about that single bond. In the same way that if you had 2 pieces of wood and you joined them together with 1 nail, you could spin those 2 pieces of wood relative to each other. As soon as you put in a second nail, which in this case is like putting in a double bond, the 2 pieces of wood are no longer able to spin around each other. Again, I'm not expecting that you'll be assessed on this, but this is colouring in our understanding and making it a bit stronger. Let's look at the bonding in benzene. Each of our 6 carbon atoms has 4 valence electrons. Now that's based on the periodic table because carbon has 4 valence electrons, and we know that from our studies in physical sciences. I'm going to build up a diagram in this bottom right hand corner of the slide right now, and it's all going to be in relation to this carbon which has 4 valence electrons, with each valence electron being represented by one of these dots. So our central black carbon here is sharing 1 valence electron with the red carbon on its left. Each of those carbon atoms is sharing 1 electron, and we have thus 2 electrons between them and a single bond formed. We're going to do the same thing with the blue neighbor on the right. We're going to share those 2 electrons, 1 black, 1 blue, between those 2 atoms. This is another single bond. Next up, we'll share the 3rd electron with a hydrogen atom. Now hydrogen only has 1 electron, and so it comes along, shares an electron with carbon, and then there are 2 electrons between them, which is a formal single bond. The 4th electron is above the plane. Benzene is a flat molecule, and if we looked at it from side on, this is what we would see. That 4th electron is above the plane for each of those 3 visible carbons, and in fact for all 6 of the carbons in benzene. And that 4th electron is free to move around all 6 of those carbon atoms, because when doing so, the amount of electron density that's on top of those carbon is maintained. What I have here is a space-filling diagram showing the distribution of electron density on benzene. This red region here is an area of high electron density, and the blue region, which should be where those hydrogens are, is an area of low electron density. So our electrons above the plane are shown to move freely in a circle around those 6 atoms in the hexagon. Because they can be shared around and move around in this manner, we describe these electrons as aromatic, and these aromatic electrons can weakly interact with things. So you can think of benzene as having a slightly polar face. This is responsible for the chemistry of graphite, where the sheets of carbon are loosely interacting with each other. It's this electron density that we're seeing on top of benzene, spread across a whole sheet of, if you like, benzenes, that allow those 2 sheets to weakly interact with each other. Not so strongly that they can't move, but strongly enough that they stay together until there's some physical force. For our course, we need to be able to draw the structure of benzene. We're going to take this structural diagram and we're going to make a few modifications to simplify things for you. Firstly, we're not going to show the bonds to hydrogen. Secondly, all of our bonds are equal, so rather than alternating double and single bonds, we're going to use a circle in the center of the hexagon. Finally, we're not going to draw the atoms. We're in fact just going to draw the bonds. You can see here, each intersection is a carbon atom, and so we've got 6 intersections moving around our hexagon. This is how we would like you to draw the chemical structure of benzene. And here we can see the original structure superimposed over the top. So why are we talking so much about benzene? Because of this aromatic bonding, benzene doesn't react like an unsaturated molecule. Instead of undergoing addition reactions like an unsaturated molecule, benzene undergoes substitution reactions like a saturated molecule. The delocalized electrons mean that benzene is described as aromatic, and that has absolutely nothing to do with its smell. It in fact refers to those electrons being free to move around the molecule. There are other molecules that are aromatic. We'll talk briefly about some of those examples in this course, but most of them you'll run into at university if you go on to study chemistry. As I mentioned earlier, those regions above the ring can interact with each other, so the region of high electron density on one side of the ring can interact with a region of lower electron density on the other side of the ring, and this is what we see in graphite. It's really unlikely to come up, but we could talk briefly about the reactions of benzene. From our understanding of hydrocarbons, we know that when double bonds are present, we have an unsaturated molecule, and that's going to react rapidly with bromine water. Benzene does not react rapidly with bromine. If we wish a reaction with bromine to occur, then we need to add an iron 3 catalyst and heat it. The molecule that we get is bromobenzene, which is the result of a single substitution reaction. We haven't talked about this reactivity before, but unsaturated molecules will react with sulfuric acid. Benzene will not react with sulfuric acid, unless you heat it, in which case you can make benzene sulfonic acid. And finally, benzene will not react with potassium permanganate, which is a strong oxidizer. This is in comparison to, let's say, cyclohexene, where if we add bromine water, we see an addition reaction across that double bond, forming the dibromo species. If we react with sulfuric acid, you can see that we don't require heat to achieve the product. And finally, if we react cyclohexene with an oxidizer, potassium permanganate, you can see that a reaction occurs. Now, this particular reaction is valid for our course because we've oxidized an alkene, and in this case, produced a dicarboxylic acid. All of these reactions are with an unsaturated species. This difference in reactivity from benzene indicates that benzene is not an unsaturated molecule. That's all we need to know in our studies of benzene. I hope it all made sense, and I'll see you guys next time.